Perfect, perfect. Okay. So feel free to jump with questions. I might not be able to monitor the chat very closely. But shall we start? I think it's a 3 of us. Yes. Okay. Let me make sure I can use. Okay, nice. Yeah. So this is a little bit of a, I don't know, maybe just a bit of a bonus lecture where I thought it would be nice to go over jet bundles again and the Tom's generalized theorem with some more details and see with more details the genericity of Morse functions and excellent Morse functions and some further examples. So there's going to be a little bit of overlap with the end of last time, but I still think it might be useful to do that. And so we introduced all of these notions last time: the jet bundles, the transversal. Oops, sorry. Okay, that works a little bit different than I thought. Sorry, 1 second. Okay, fine. The transversality theorem and also sketched how to derive the density of Morse functions. Today I want to talk about these again. I want to talk about generic maps to the plane, and also in the end we're going to get a bird's eye view to Tom Boardman theory. And tomorrow we'll talk about generic paths of smooth functions, which I'm calling Cerf paths here. I'm saying recall our broader goal is to calculate this relative fundamental group. This is the space of all smooth functions on M, and this is the space of all smooth functions on M without critical points. I say this is our broader goal. We can maybe, for the most part of today, forget a little bit about this goal, and towards the end, it might come up again. So just remember that a K-jet is this data of an equivalence class of a triple, x, sigma, y, where sigma is a germ, and the equivalence class is so that we only keep track of data of the partial derivatives up to order K. That's what the equivalence class gives us. And we defined last time these sets of this like K-jet sets JK of M comma N to be the set of all K-jets. It has a structure of a smooth manifold, and we have 3 different projections that we can write. It's the projection to the M factor, the projection to the N factor, or to the N cross N factor, which comes from the fact that points here are equivalence classes of triples, where the first part is a point in M, and the last part is a point in N. And we said last time that these things are fiber bundles, and moreover, if I look at the K-jet space of Rm and Rn, this has this canonical splitting into Rm cross Rn cross the space of degree K polynomials with n variables and coordinates. Okay, and this is basically, so this is the identification that we use. Did I erase anything? No. This is the identification that we use in order to obtain an atlas for the K-jet space of M comma N that gives the manifold structure here. The thing that I'd like to correct from last time, I was half imprecise and half completely wrong. So we had this thorough discussion of what is the actual structure that these bundles have. And let me say what's happening in general, and then we can see what's happening in specific cases. So in general, if we have this fiber bundle here, as we kind of saw from this identification, the fiber of this fiber bundle is the space of K degree polynomials. And the structure group ends up being this interesting product of groups. So what's GL upper parenthesis K of M comma R? The definition is it's just the product of the general linear group And with this funny thing here, which I guess it's a product of the space of symmetric polynomials in R variables and R coordinates. So basically, we have these groups which have a linear part to them and a non-linear part to them. You'll see just by how this thing is defined, it's just like this product from J equals 2 to K. If K equals 1, the non-linear part isn't there. There's only the linear part that stays, and we get the structure of a vector bundle. So J1 is a vector bundle, and then when K is greater than 1, this here, I mean, just doesn't have the structure of a vector bundle anymore. It has a structure of a fiber bundle. And I don't really have a very like enlightening sort of like thing to say about how this comes up, other than you do the calculation of the of what the coordinate changes are in this fiber bundle, and that's what ends up being. If you don't want to do this calculation, or if you just want to read about it, I think like a very good reference where I found this is chapter 1 of this book, Manifolds of Differential Mappings by Michor, where he does it in a lot of detail.
Let me also just say, Dario, that book by Michor is also the reference for, or at least maybe that book or a similar book by Michor for infinite dimensional manifolds. He's got a very nice
okay, cool. Thank you.
I mean, that might be, because I think in this book he very much talks about spaces of differential mappings, which usually are infinite dimensional manifolds. So that might be, that sounds reasonable. Okay, and then the other thing is if we consider, well, so here you see we consider this fiber bundle where the base was m cross n. If we just consider the fiber bundle that we get where the base is just m, so we just project in the m direction, and n happens to be Euclidean space, the fiber is Rn across the space of polynomials, but actually always going to have the structure of a vector bundle. So the coordinate changes are actually linear in the fibers, which is pretty interesting. So yeah, that's just, I was imprecise and also wrong about J1 last time, so I just want to like put out here what's known about the structure of the KZ spaces and where you can find
it. I mean, the KZ spaces are very, very cool, and somehow, I mean, I'm only learning it from now in a deeper way through what you're saying, and somehow to me they're so fundamental that they deserve to play a more prominent role in books on smooth manifolds. Yeah. You don't see it written down in a lot of places.
That's true. Yeah, I mean, Michor does a great job, but I also kind of like run into it like random. Like I was, but I agree. Yeah, it's not as easy to find a good reference on them as one might hope. And last time we ended with celebrate theorem of Thom's jet transversality theorem. So just as a reminder, this says that if M and N are smooth manifolds and W is a smooth submanifold of the KZ space, then if you look at this collection of maps, which I'm calling TW, which is the collection of all smooth maps from N to N, whose KZ section intersects W transversally, this is going to be a dense subset of C infinity M comma N. I should say that the actual theorem, you won't maybe find it written down like that. You would say that it's a residual subset. Residual meaning that it's countable intersection of open dense subsets. But this space, C infinity M comma N, has this property. It's called a Bayer space, and this property says that anything that's residual is actually dense in it. So, but I should say, and one thing that I didn't say last time is that we don't automatically get open and dense. We only get dense, and TW is going to be open if, moreover, we have that W is a closed submanifold of the K-jet space.
Just for posterity, that JF, maybe just make it clear that's a JKF there. It's a little bit.
Yeah, that's an R. Yeah, you're right. Thanks. That's good catch, Bruce. Yeah. Okay, that's right. So is that relatively clear? We're gonna see. I think today we're basically gonna spend most of the time just saying applications of this and like carrying it out with examples, because that's the only way I can sort of understand what's going on. And we're also going to define or provide a variant of this, which is called the multi-jet transversality theorem in a bit. But I just wanna, that's something that we mentioned last time, but I think it's worth doing it in detail because the argument is quite nice. And it's worth spelling out in detail. So I just want to prove in detail that Morse functions are generic. So the space of Morse functions is open and dense in the space of all smooth functions. Okay, and the thing that we are going to focus on, we're going to focus on this first jet space. Now, if you give me a representative of a class in this first jet space, I can take the differential of the germ at X. The equivalence class keeps enough information for me to be able to do that, regardless of the choice of the representative. So, but this is just a linear map, right? It's a differential, just a linear map between vector spaces. And if you give me any linear map, it has a rank. In particular, if you give me two vector spaces, there is a maximum rank that a linear map can have between them, right? And that's just the min of m comma n. Okay, I just can't. The rank of a linear map cannot exceed the minimum of the dimensions of the vector spaces.
Let me just pause there because so what was confusing me and what still confuses me, I must just think about this but it's just, this is really nice. So from a sigma you can extract out its first derivative, but to me you should be able to extract out something invariantly up to its kth derivative. But I just wouldn't know how to write that down exactly. So for example, the first and second derivative information is also some kind of linear map from tensor powers of Tn to tensor powers of Tn. But I'm just trying to figure out exactly what that is. You know what I mean? Like you shouldn't just be able to extract out the first derivative. You should be able to extract out the entire thing in an invariant way somehow.
I mean, okay, so I mean, right now I'm just working at the first jet space, but what you are referring to is if I had the K jet space.
Yeah, I mean, because clearly d sigma is a function from the kth jet of anyway, no, I have to think this through, but it's if I was working in the K jet space, I should be able to extract out some kind of linear map from somewhere to somewhere.
I think you should be able to extract like you should be able to extract the partial derivatives up to the K if you are a K jet.
Just so have to write that down invariantly as a linear map to 10.
Yeah. Yeah, I mean that goes into how do you write invariantly.
Yeah.
The K partial derivative is a linear map.
Yeah.
I'm not sure I know how to write it.
But yeah.
Yeah.
I'm just flagging that as an issue.
Yeah. It's a good. No, yeah, definitely. But here all I'm basically saying is that if you just give me like any linear map between this vector space and this vector space, the maximum possible rank you can have is the minimum of the dimension of m dimensional. There isn't just room for anything else. So, and that's a more general thing. I mean, if you just give me an m-dimensional vector space and an n-dimensional vector space and a linear map, if Q is the minimum of m comma n, I can define the corank of F to be just Q minus the rank of F. Or I can, like the same way, I can just define the rank of F. Oh, no, well, sorry, the rank of F has a definition already, but I can say that the rank of F equals Q minus the corank of F, which is what informs this terminology here. We will say that F drops rank by R if its corank is R. So if my linear map just fails to acquire the maximum possible rank it can acquire, the corank keeps track of how much did it lose, roughly. And so if you give me now any smooth map, I can define a locus for you. So if you give me any smooth map, I can define this locus SR of F. This is a locus of points in M, and consists of all those points where the differential as a map from the tangent space of M at X to the tangent space of N at F of X drops rank by R. Okay. Just looking at the collection of all those points, I'm not making any statement as to whether this collection forms a submanifold or not, just a subset of points in M where the differential of the function I'm looking at drops rank by R. And similarly, so that's at the level of a function in the manifolds, but similarly, I have something at the level of the first jet space. I can define S sub R to be the subset of the first jet space that consists of those jets that drop rank by R. So far, I haven't really done anything. The first time where you do something is where you have this theorem, which says that SR is actually a submanifold of the first jet space. And also, the theorem tells you what well, I guess the codimension of this submanifold is. And its codimension is going to be given by this very nice and simple formula, which is R squared plus R times the difference between M and N. Okay. I'll let you absorb this for a second. It's not something that I'll prove. I want to use this sort of as a given, but one thing that I'll just say is that this is a statement. So J1, as we said, is a vector bundle. But this is the statement that if you want to prove, you don't need to work at the level of vector bundles, you should work at the level of vector spaces. Because nothing that I said really depends crucially on the fact that we are working in families. So I can, if you give me any vector spaces, V and W, and this home set is like, I guess, in fact, maybe I should say home vect here. If you look at like all linear maps, you can look at the subset of all linear maps, which I'm calling here L to the R, the subset of linear maps that drop rank by R. This itself is going to be a submanifold. Yeah, these spaces all have a manifold structure because they're vector spaces, right? And this is going to be a submanifold with the codimension given by the same formula. And that's how you would like prove this theorem by working the level of vector spaces. So this amounts to being a linear algebra problem. It might not be it's actually not a very complicated linear algebra problem. yeah, I'm not going to do it. But Gilliman and Golubinsky, they have actually two different proofs of this, which are quite elegant and worth saying. Just all I want you to remember is that we can construct those submanifolds of the first jet space, and we know that there are submanifolds, and we know what their codimension is. Okay. And actually, it's a little bit stronger than that. We don't just know that they're submanifolds. We know that they form a subfiber bundle. So if I look at this projection to m cross n from the first jet space, and I restrict it to these SRs, that defines a map from SR to m cross n. And this is a subfiber bundle. Well, remember that the fiber in this, well, vector bundle is home from Rm to Rn, and the fiber of the subvector bundle would be this LR from Rm to Rn.
Very elegant.
Yeah, so it's basically, you know, what you can wish for works, which is one of those moments. Yeah. Let me pause for a second and ask how are we doing, because it's a little bit, I introduced, this is a talk which unfortunately is not going to have as many pictures as the previous ones. So I want to give us some moments of breath, because I introduced a lot of new stuff.
So, okay, is this yes, that drop R from Rn to Rn or from M to N?
This is from Rm to Rn. So I haven't. Yeah. So Rm and Rn, they are vector spaces, and I can write down home from Rm to Rn, which is the space of all linear maps from Rm to Rn. And this guy here is the subspace of this guy, which consists of all those linear maps from Rm to Rn that drop rank by R.
Yeah, but when I thought to be like from M to N, not from Rm.
Sorry, yeah. So M and N are manifolds. So I couldn't actually write. Like, this doesn't. Well, I guess if you wanted, you could define something like that. But at least the way I defined the LRs, this wouldn't actually work, because the LRs are just, well, their input is vector spaces. But the way you get that is, remember what this thing was. So this thing is basically M cross N. Well, actually, sorry. Let me just say, what is the fiber? So if X is a point in M and Y is a point in N, what is the fiber over X and Y? It's basically the space of all linear maps from TXM to TYN, right? And that's the same thing as home from Rm to Rn, which is where the Rm and the Rn show up.
It's very elegant. So that's the proof. That's one of the two proofs in Goleman that Golubinsky use the singular value decomposition. Because there's this cool fact, which is that, okay, so this space, the space of So LR it sits as a sub-vector space of all linear maps from R into R maps. It's actually a subspace, not just a subset of that linear.
Well, it's a submanifold in particular. Besides,
or is it just a submanifold?
What do you want it to be?
I was thinking that it's a subset. I mean, a subspace, but it's not a subspace, right? Because we take two maps that lower the rank by R, like two linear maps. You add them together, then they might not lower the rank by R. Like, for example, if you subtract one from each other, then you get the zero map, which probably is a bad thing.
Lowers the rank by a lot.
Okay, but anyway, there's this cool fact when I learned about singularity compositions that nevertheless it's a submanifold of the space of linear maps, right? And you can take a linear map and you can orthogonally project it onto the submanifold of things that lower the rank by R, something like this, and that amounts to taking the singular value decomposition of your linear map and just restricting to the first R singular values or something. There's some nice construction like that.
We should, we should see it again. I mean, I don't. I haven't recently gone through like the proof of that, so I don't remember. I don't remember this being mentioned, but yeah, we should just do it afterwards. I think it's should be interesting. Yeah, it's not. Yeah, we'll have to see afterwards.
Okay. Yeah, it's nice. It's very nice. I like it a lot.
It's good when things work out the way you want them to. Yeah. But any other comments, concerns? Yeah. Right. So J1 of m comma n. Now, so that is well, that is a space that goes back a little bit to it's a space of all one jets from n to n. So one jet is well, you can think of it as just a triple of a point in m, a point in n, and a linear map from the tangent space of m at that point to the tangent space of n at that point. So you can think of J1 as such a triple. Yeah. You can roughly think of it. You can think of it like that. The actual like the actual definition would be that it's like an equivalence class of triples where you have x, y, and a germ. So it's just a function basically that sends x to y, but where the equivalence is that you would take any two functions to be equivalent if their partial derivatives up to order k agree at x. So basically, the only thing that you keep track of is really the partial derivatives up to degree k at x. And that's for the k jet. For the one jet, that's just the differential single partial derivative. I don't know if that helps. Does it help? Yeah. But yeah, in practice, it's just x, y, and an element here. Okay. Shall we see some of the implications of the things that we defined so far? So the first implication is, like I defined two things for you. I defined SR of F, and I defined SR. SR itself doesn't refer to like any function F. SR itself is a submanifold of the first jet space, right? And so the first implication is just by definition, basically, if an element X in M happens to live in SR of F, well, what does that mean? It means that the differential of F at X drops rank by R. Well, that's exactly what that exactly says that if I look at the first jet section of F at X, I mean, what is this? What is this thing? This thing is just the triple X comma df at X comma f of X. So this is going to drop rank by R. That's what this condition says, which implies that this triple lives in SR. Okay, because that's how we define SR. Yeah.
Your J superscript 1, the one almost looks like a sort of perpendicular symbol.
Yeah, that's that's one of the things that people who know me need to adjust to. I can yeah, I can.
No,
I don't know if does that help. Yeah, they also. I mean, my ones sometimes look like the two, look like what other people would say is 2.
Okay.
And so that's also a bit of a confusion. Yeah, and I should say if you read Mihor actually, because so his L's look very much like my ones.
Oh,
so for a very big for a long time I was reading through him and I thought that he was exclusively worrying about one-dimensional vector spaces, whereas he was actually doing constructions on L-dimensional vector spaces. But I mean, it did become obvious from the context quite early on. But yeah, so that's yeah, but today, like, all our jet spaces are going to be either 1 or 2, and you'll see when we get to the 2, it's not going to happen soon. So yeah. So is this one clear? And then let me zoom out a little bit to fit more into the page. Yeah. So S0 is always going to be a codimension 0 submanifold of J1, because if I put R equals 0 here, I get 0 back. So and then the other implications is if I take my target manifold to be one-dimensional Euclidean space, then S1 will be of codimension will be of codimension 1 plus 1 times minus 1, which is just M. And SR, if R is greater than 1, from the same formula, will be of codimension sorry, I made a mistake here. It doesn't affect what I actually want, but that should be R squared. So this is no longer true, but this is definitely true. Okay. So and so basically, like what I deduce from that is, if my first jet section of F intersects SR transversally and R is greater than 1, that means that it must intersect SR vacuously. Because if it didn't, if it had a non-trivial intersection, then we would know by the transversality theorems that the pro-image of this intersection would be a co-dimension SR submanifold of M. But see, the co-dimension of SR is bigger than the dimension of M, so I can't have that if R is greater than 1. Yeah. So the
it's all about arguing about the empty set.
yes, it's just I'm just saying, suppose that this here wasn't empty. Like, let's suppose that, I don't know, suppose that J1F intersected SR in something that I'm calling W, okay? I mean, recall what the setup is. We have J1 M comma N, we have M, and J1F is this map, right? So so by transversality, the transversality assumption would imply that if I look at J1F inverse of W, that would be a submanifold of M. I don't know, call it X. And also, the codimension of X in M should equal the codimension of SR, the thing that I intersect transversally, in J1 M comma N, which is where I intersected. That's like one of the, like, I guess, central theorems in that make transversality quite a useful and important notion. But here we calculated the codimension of SR. The codimension of SR we calculated to be something that's greater than the dimension of M. So, well, dimension of M minus dimension of X must be greater than the dimension of M. That's a contradiction. There's no way I can have that. So the only way that I can have transversality, the only way J1F can intersect SR transversally, is if it doesn't intersect at all. Because otherwise I would have this, for dimension reasons, this problem.
Is this one because I'm trying to look at this one, then I'm in this book, and then the theorem.
Which one? Yeah, that's a different Transversality theorem.
Yeah. Is it what you use?
So do you mean Tom's Center? Yeah. No, it's a different. Yeah.
So which theorem do we use to say this?
Let me just say it. Let me make a new page here. Yeah, it's actually quite a nice theorem. So if f from x to y is smooth, and W is a smooth submanifold of y, such that F intersects W transversely, then F inverse of W is a submanifold of X. And furthermore, the codimension of F inverse of W in X must equal the codimension of W in Y. Huh? Yeah, exactly. This is one of the things that makes the notion of transversality really, really nice, because in general, it's not true that if you pull back submanifolds, you get submanifolds. But if you intersect them transversally, then you can pull them back and you get submanifolds. And you furthermore know exactly what the dimension of the, well, I guess the codimension is the dimension of the submanifold there is. So that's the theory. Please. This one? Yeah. Yes. That's the thing which I'll explain to you with like 3 pictures, and then with the formula. So sorry. So this here is an example of a transverse intersection of a line with a circle. This here is an example of a transverse intersection of a line with a circle. And this here is not, well, okay, this is supposed to be a tangent, is not an example. So, so roughly, an intersection is transversal if if I perturb it a little bit, I'm not going to change the number of points that have intersected. So here, if I perturb this line a little bit, I still intersect in 2 points. Here, if I perturb this line a little bit, I still intersect in no points. Whereas here, if I perturb this line a little bit, I will either intersect in 2 or in 0 points, which is different than what I'm currently intersecting, which is 1. It's kind of like a notion of like generic intersection in some sense. And if you want if you want maybe a precise mathematical definition, is that F will intersect W transversally at P if looking at the image at P of the tangent space of M direct sum with the tangent space of W at F of P gives me the tangent space of N. Yeah, the only caveat is that I have to use X and Y because. So that's like the definition of what it means for F to intersect W transversally at P, and then F will intersect W transversally if it intersects W transversally at P for every P. But that's the picture to keep in mind. The definition. Yeah. Okay. So are we happy that the first jet section? Yeah. Okay. Now for so what's happening? So the thing that I claimed last time, but I'd like to prove in some detail is if the first jet section of F intersects S1 transversally at X, then that is equivalent to X being a non-degenerate critical point of F. It's not.
Yeah, very nice.
It's. I kind of waved my hands last time, but I think it's a beautiful argument that requires sort of do it quite explicitly. So I'll do it in gore detail. And first we're going to need a lemma, which is it's a very cute lemma, and it compares the transversality condition with the condition of being a submersion. So recall that a smooth map is a submersion at X if the differential is a surjective map. And being surjective implies actually that it's a full rank. And also let me make the comment. If you look at the definition of being a submersion, it's the same with if you consider F of X to be a zero-dimensional submanifold of N, it's actually exactly the same condition as requiring F to intersect F of X transversally at X. Like if you unwind the definitions, that's basically what you will get. So I don't know, it's just a fun observation, and also in particular, if you believe in this theorem, you get maybe a proof. Well, there are proofs where directly you just use the notion of submersivity, but you get a proof that if your map is a submersion at X, then well, actually, no, let me not say what I was about to say because it's not right. So that's the only observation I wanted to make. Now, the setup that I want to consider is the following. I want to consider like a sequence of smooth maps. And it's a map from M to N, which is smooth. And then it's another map from N to RK, or some K, calling it F and Phi. And these maps, I don't know, send some point P to F of P and then F of P to 0. And the broader question that I want to ask is, if this map phi is a submersion at F of P, then when is the composite, when is phi composed with F a submersion at little p? That's the question I will ask. So, okay, this is what you get for introducing an extra page, but the slide discontinuities, but it's okay. I remember what we want to ask. That helps. Right. I mean, in general, it's not true that if this is a submersion at a point, you don't have any reason to expect the composite to be a submersion at a different point. I mean, a priori, you just don't have any reason to expect that. But the lemma says that if given that phi is a submersion at f of p, oops, sorry, the composite is a submersion at p if and only if f intersects phi inverse of 0 transversally at p. I put that in quotation marks because, strictly speaking, it's not entirely correct. See, the and this is the same mistake that I was about to make when I just stopped myself from carrying on what I wanted to say. But the reason why you would expect this to make sense is that if phi is a submersion at f of p, then you would expect, basically from this like transversality condition that I just said, would expect phi inverse of 0 to be a submanifold. Therefore, so you can make sense of this thing that I wrote here, f intersects f inverse of 0 transversely. But that would be true only if phi was a submersion of the full pro image, which I don't actually have. Like, I don't know if phi is a submersion in the entire phi inverse of 0. So that's why I put this into quotation marks, because technically speaking, phi inverse of 0 is not necessarily a manifold everywhere. But what I do know is that there should be a little neighborhood around f of p, such that if I restrict phi in that neighborhood, I get a submersion throughout the entire neighborhood, and therefore I can pull back 0 into that neighborhood and get a submanifold that lives within that neighborhood. I don't know if what I just said made sense,
it
but
might be easier that I think you wrote in inverted commas. It might be easier just to write it out explicitly at the middle of the tangent space. So it's just saying, it's an explicit condition at the middle of tangent space.
Yeah.
And then you wouldn't have to worry. Then you can specifically pick which tangent space.
That's true. Yeah, that's true. I somehow really liked this statement as it was stated, and so I just wanted to, because morally that's sort of
morally,
so Gilliam and Golubitsky, they wouldn't, you won't see that written here. They're like that for a good reason, because it's not true. But I sort of wanted us to think of it like that. And basically, like, just the first part of the proof is just saying what I just said. It's just like making this sort of precise. If you are a submersion at f of p, there should exist a coordinate chart in N centered at f of p, where phi locally takes this form. So like all submersions locally look like projections, standard projection from n-dimensional Euclidean space to k-dimensional Euclidean space. That's the local form that they all take. So in particular, phi will be a submersion in this neighborhood around f of p, and I can consider W to be f inverse of 0 intersecting that coordinate chart, and that would be a codimension K submanifold of U, and I guess therefore, well, question for the audience: why is the codimension K submanifold? Where did this K come from? we give it away, it's basically, I mean, it's this theorem that I introduced here again. But now W is a single point. It's the point 0 in Rk, and the codimension of the zero-dimensional manifold is just K. So that's where we get the K. Okay. So is it at least relatively clear what we are trying to prove? Like what does the lemma say? Let me prove it for you, and that might help as well. Okay, so the first thing to notice is that for dimension reasons, I'm saying here that the kernel of the differential of phi at f of p must equal the tangent space at f of p of w. Well, basically, so why is that? Well, I mean, if I restrict phi in W, that's just the zero map. So everything, so I have an inclusion like that.
Well, I mean,
and then
W is just is in code. That's just when the other coordinates, right?
Yeah, exactly. I shouldn't spell that out more, but yeah, that's exactly that. And now it's a matter of unwinding definitions. So if F intersects W transversally at P, just what this means from the definitions, it means that the tangent space of N at F of P must equal to the direct sum of the image of the tangent space of M at P under the differential of F with the tangent space F of P of W. And I'm just rewriting now, and I'm putting where tangent space at F of P of W, that's the same as the kernel of the differential of phi at F of P. And now this equality here, that's exactly the statement that the differential of the composite phi with F at P is onto, given that the differential of phi at F of P is onto. Because given that the differential of phi at F of P is onto, the only way this guy would fail to be onto is if there was some vector in the image of df that was killed by d phi. And there is not going to be any such vector because of this decomposition, given by the transversality. So that's the claim. How does that feel?
I would have to just sit down and just draw out some pictures, but I understand what it's saying. Yeah.
Okay. Yeah, we'll just use the
Brian,
statement.
use it in there. But
fine. Okay. Let's see it in practice a little bit, and then we can go. Yeah, let's see it in practice. So I want to apply this in the following case. Yeah. I want to look at M, and I want to look at the following sequence of maps. There is a map which is the first jet section of F, and the target of it is J1 M, R. So this is going to be the N here in that lemma. Now, this first jet space, we saw that it's basically M cross R cross the space of linear maps from Rm to R. That's just an identification. So now I get a projection map, which is in particular a submersion. But I get a projection map to the space of all linear maps from Rm to R, which I can identify with Rm. So this is the sequence of maps, J1F and pi, sequence of maps that I want to apply the previous lemma to. Let's see how to do this. So what is pi inverse of 0? Oh yeah. Yes. That's yeah, sorry. The claim is that J1F intersects S1 transversally at X if and only if X is a non-degenerate critical point of X. Yeah, that's a good point. I made the mistake, which is good when you write it, but not good when you present it, which is I'm doing like a nested lemma inside another lemma. But yeah, that's what we're actually trying to prove. Yeah. And now I need to make these things appear. Okay, so so here, remember in the nested lemma, I had pi inverse of 0 appear. So pi inverse of 0 is just S1 for us. This is just the subspace of J1 where this derivative here is 0. Okay. So what this lemma says is that J1F intersects S1 transversally at X if and only if the composite pi with J1F is a submersion of X. That's what the lemma we just proved says in this setup. Okay, now what is pi composed with J1F? That's just the differential, right? So that's partial f with respect to x1 and all the way partial f with respect to xn. Because that's what, like, remember what J1F does, right? It sends x to this triple x, comma, f of x, comma, the differential of f of x. The differential of f of x, if I choose some local coordinates, is just that.
Okay. Yeah, it's very elegant.
And now, well, when is this map going to be a submersion? This map is going to be submersion precisely when its differential is non-zero, but the differential is non-singular. But the differential of this map is just the Hessian. It's just the second derivative matrix. And the Hessian being non-singular is exactly the non-degeneracy condition. So that's where.
Yeah, that's very elegant. Yeah. You see, Brian, what he did is he took the function f. He took its first jet, and that became a new function with the function associated to x now, the partial derivative of it. So that's now a new map between those functions. You can take the derivative of that, first derivative of that new map. And the first derivative of that new map, the same thing as like the matrix of second derivative of the original function. So that's matrix of second derivative, the S, that being non-singular, is what we usually say, but the function being non-degenerate. Critical point. Now we're saying that we boil that down to a condition on the first derivative of this new map. So that it has to be a subversion. Yeah.
Exactly. And now we just apply Tom's jet transversality theorem as a hammer. I mean Tom's jet transversality theorem tells us that the space of functions from M to R whose first jet section intersects S1 transversally is dense. We've just identified that those functions are exactly the functions with non-degenerate critical points, namely the Morse functions. And so we conclude that the space of Morse functions is dense in C infinity m comma r. And I should say for open, just see that like S1, the way we defined it, I guess is a closed submanifold of J1, and so we get the open and dense part of the transversality theorem. But yeah, how does it feel? I mean, I think this is a good point to pause for a break. I'm a little bit overdue of the break, but please ask questions.
Maybe just spell that out explicitly. So when you say that this map is a submersion, exactly when its differential is non-singular, just explain that. So we have got a map.
Well, I mean that's true for any map, right? The differential, like being a submersion, basically means that it's a full rank.
Full rank. Not non-singular is sort of saying it's not invertible. Like that's the right word to use. Don't you mean full rank?
I mean full rank, and I believe that full rank in the case of Hessian means that it's non-singular. Am I wrong here?
So all I'm saying is just take that map there, and then so now we're supposing that then we take the so for this map to be a submersion, it means that the derivative of this map is a surjective linear map.
Yeah. Mm-hmm.
I would just like to see why that's equivalent to you saying the matrix of second derivatives is invertible. But that's the definition of non-degeneracy.
Yes. Well, because there's two claims here.
It sort of seems obvious in my head, but I just like to see it. Yeah.
Do you see? Like, are you happy that the derivative of this map is the matrix of second derivatives?
I agree.
Yeah. And then I believe it's. I mean, if you give me an n by n matrix, and that matrix is a full rank, then it's going to be non-singular, and vice versa. If it's non-singular, then it must be full rank. So it's
So the point is that the whole point is that when you got a Morse function, it's not a very geometric thing, because you're saying that where you at the critical point, the matrix of second derivative is supposed to be invertible. But that's not a very differential geometric way to state things. It's not an invariant way to state things. And what this thing is saying is that the right invariant way to say that a point is a critical point is to say that the J1 is a submersion at that point. That's a nice invariant way to say it. We don't have to talk about the matrix being invertible. Yeah.
We are going to see later another way you can set things up in a coordinate-free fashion. But not as
So, then we show that the space of Morse functions are open.
Yes, well, that's a first step from like many to follow that will be assembled together. But do you mean in general what's the importance of that, or like specifically for the pseudo-isotopy theory?
In this case, like for the space to be open, the significance of that.
For I guess an immediate application is that it's non-zero. So Morse functions exist in a manifold. That might be not the most direct way to show this fact, but at least you can be happy that Morse functions like exist in a manifold. But also, I guess most crucially is like there is an abundance of them. So if you give me any smooth function, I can just perturb it a little bit, and I can get a Morse function in the end. So there is like, and any smooth function out there lives very, very, very close to a Morse function, at least morally. That's what this like open and dense condition would tell you.
And M is endless movement.
M is any smooth manifold. So for any smooth manifold, first of all, I can construct a Morse function, and second of all, any smooth function I construct is in the space of smooth functions, like arbitrarily close to a Morse function.
That's very good. Let's have a break.
Let's have a break.
Yeah.
Yes. If there are any questions from online participants, also feel free to let me know. Yeah. But I'll mute this here because we're having a 10-minute break. Okay. Okay, can you hear me? We are back. Maybe that was okay. We got a thumbs up, so I think Barry can hear us. Yeah, we might go slightly over date, but I'll try not to keep us here for too long. Since I wanted to devote this into like a Tom jet transversality day, I thought it might be nice if I also show you the multi-jet transversality theorem and show you how we can use that to then deduce that the space of excellent Morse functions is open and dense. It might be a bit of an overkill, and we don't like strictly speaking need it. There are other ways you could get that, but I don't know. I thought it might be nice since we are in this mode to like sort of like see everything there is to see. Or I guess I can take a vote because that's one thing we can do, or I can apply the single jet transversality theorem to another example, which is pretty cool, and then move on to something else. Is there a preference? It's a hard thing to ask because you haven't seen either of those things. So let's carry on with the way. Let's carry on, and then we'll see. So I just need to set something up a little bit before I tell you what the multi-jet transversality theorem says. And that's, well, if you give me a smooth manifold X, I can consider its S-fold Cartesian product. So nothing fancy going on here. And I can also consider, I guess, a subspace of the S-fold Cartesian product, which is the configuration space of S points in X. And that's basically just S tuples, x1 up to xs, in the Cartesian space, with the property that xi is different than xj if I is different than j. Okay. So that's usually called the configuration space of S points in X. I don't want any of the 2 points to be the same in the S tuple. And now if I consider this Faber bundle that we all love by this point, or hate, I don't know. Well, I can always get an induced map on S-fold Cartesian products. Nothing fancy. And what I'll denote by J uppercase sub S of Mn, that's going to be the pro image the pro image under this map of the configuration space of S points in M. So basically what I'm doing is that I'm taking the S-fold Cartesian product of the K-jet bundle, but I only keep S tuples that have different base points. So pairwise, the base points in the S tuple must be different. And that's what's called the S-fold K-jet bundle of M and N. And the multi-jet bundle is some S-fold K-jet bundle. That's just what multi-jet bundle is. Sorry. And if you give me a smooth map, well, if you give me a smooth map, I can consider its, I guess, S-fold K-jet section. That's going to be a map from the configuration space of S points in M to the S-fold K-jet bundle of M and N, and it's just given by the only formula it can be reasonably given by. the multi-jet transversality theorem is just, well, take the transversality theorem and substitute S-fold kj bundles wherever there are kj bundles. So it's the statement you would get like that. So you have M and N smooth manifolds, you get a submanifold of the S-fold kj bundle, and you look at the collection of all smooth maps from M to N whose S-fold kj section intersect W transversally. That's going to be a dense subset of the space of all C-infinity maps from M to N. And furthermore, if W is compact, so get a slightly stronger condition, TW will be open. That's what the theorem says. Okay. Let's go directly to an application. So the application is that the space of excellent Morse functions is an open and dense subset of the space of all smooth functions from M and N. Remember that a Morse function is excellent if you won't be able to find two critical points with the same critical value. Okay. How are we going to do that? Well, let me have you look at the theorem up here. So I'm gonna concentrate in the case when our N is just one-dimensional Euclidean space, and I'm going to look at k equals 1 and s equals 2, and I'll have to tell you what I'll take for W. So stay with me for this. So W is going to be basically S1 cross S1, but it's going to be a subset of S1 cross S1. And it's going to be a subset where the R coordinates in this tuple are the same. So the way I would, I guess, formally write that down is if I look at pi R2 inverse of the diagonal. So the diagonal in R is like just the tuples of the form x comma x. And I look at the pro image under this projection, intersect that with S1 cross S1.
How do I know that's a manifold?
That's a good question, and it's because I'm projecting. So this map here, pi to R, that's a submersion. It's like, you remember how we just have what J1 is. Yeah. Sorry, that's. I mean, it's like. I guess I wrote it down here in generality, but let me spell it out. Pi to R, that should be a map from J1 M comma R cross J1 M comma R to R cross R. It's like pi R is a map from J1 M comma R to R, and pi R is again a map from J1 M comma R to R. So just the induced map on the twofold Cartesian product. And pi R is a submersion, just a projection to the R factor. And so pi R2 is a submersion, and this is a submanifold of the target, so it's going to be a submanifold when I pull it back. And then I intersect, and S1 is a submanifold, so S1 cross S1 is a submanifold. And
intersect transversely.
That's true. I'm being a little sloppy. That's true. Yeah.
But yeah, because like all these arguments come down to, you have to check that that the set of conditions that you're placing on F, like the where it can fail, is actual submanifold. Oh, anyway, this is cool. I'm doing.
Yeah. Okay.
So, I'm keeping you.
No. Please do. This is more fun this way. But that's what I'm going to take for my W. And what is the multi-jet?
That's like, just to be clear, that's the set of functions where the critical points do at the same level.
Yeah, exactly.
That's what W.
Yeah, exactly. And basically, we're going to make an argument that the only way you can intersect W transversely is if you don't intersect at all. It's like the usual transversality arguments from dimension reasons. That's basically what's going to be. So the multi-jet transversality theorem will tell you that a collection of all smooth maps, real valued maps, where their twofold first jet section intersect W transversally is a dense subset. And so what's the dimension of W? Right, the dimension of W is it's almost the dimension of this guy. It's almost the dimension of S1 cross S1. So like twice the dimension of S1, but -1 because here, each of these S1s consists of triples, where the last bit of the triple is a real number, and here we take tuples of such triples, but ask for the real number in the end to be the same. So we just lose one degree of freedom. So if I didn't take this intersection, I would have that the dimension of W is twice the dimension of S1. Now I will have it to be twice the dimension of S1 minus 1. Okay? That's true for the dimension of W. What I want for the transversality theorem is the codimension. And that just, so I get codimensions from subtracting dimensions from something. So the -1 will become +1. The codimension of W is twice the codimension of S1 +1. And the codimension of S1 we saw like previously is the same as the dimension of M. That's twice the dimension of M plus 1. Well, twice the dimension of M is the dimension of the configuration space of 2 points in M. Okay? And J12 of F, remember, is the map from this configuration space of 2 points in M to the twofold one-jet bundle from M to R. So W is something that lives in here if J12F intersects W transversely, and W has codimension greater than the dimension of the base, then the only way this can happen is if it intersects W vacuously. And that just, by the multi-jet theorem, directly implies that the space of functions that don't have 2 critical points with the same critical value must be dense in C infinity f comma R.
There's something that's confusing me here. Where did we use the second jet of the function, the 2 jets? Actually, we were using the 1 jet. Sorry,
we're using one jet.
We're using the 1 jet of the function, but on the configuration space of 2 points.
Yeah, exactly. Yeah, the 2 exactly. The 2 doesn't refer to jet dimension. It refers to.
I mean, the reason why we needed to have the configuration space of 2 points, those were the 2 points that were causing the problem. They had their critical points at the same level. That's why we had to use this language. I'm talking about the multi-jet transfer because we needed to have the geometric situation where we could talk about 2 points at the same level.
Because you can think, like, if you unwind the definitions, and I should have done that, sorry about this, but you should think what it means for J12F to intersect W at all. Like, leave transversality out of the picture. What does it mean for J12F to intersect W if W is defined like that? It means that you have because J1 to F is a map that has input the configuration space of 2 points in F. So what's going to take as input is x comma y, where x and y are different points in F. That's the input. Okay, and what's going to be the output? The output is going to be something in W. So being in S1 cross S1 means that both of these points are critical points. It means that their derivative, the derivative of f at those points vanishes. That's the S1 condition. And being in the pro-image of the diagonal of R means that f of x equals f of y. So J1 to F intersects W precisely if M has two distinct points that are both critical points with the same critical value. And we just proved that this cannot happen if we impose a transversality condition. So now you might say that we're not entirely done, because see, you might be tempted to say, oh, I didn't actually need the single jet transversality theory. I could just like state the multi-jet transversality theorem and directly get that the space of excellent Morse functions is dense. But actually, I think it's a little bit like what we strictly speaking proved here is that the space of functions that don't have two critical points with the same critical value is dense. But I didn't tell you anything about the quality of those critical points. So this is a statement where I never said anything about those critical points being non-degenerate. So I actually have to intersect this space with the space of not necessarily excellent Morse functions, and then the intersection of the two will be the space of excellent Morse functions. Now, if I just intersect two dense spaces, I don't necessarily get a dense space. But if one of them happens to be open and dense, then the result will be dense. And so that's how like it all nicely comes together. So if I love it. Yeah. Yeah, no, sorry. It's a bit of a
Look, I'm reading this sentence.
Which sentence?
This one of the function that doesn't have two critical points.
Yeah.
Critical
Mm-hmm.
ends in its most function.
Yeah.
I don't understand this with the function that doesn't have two critical points.
The space of functions.
Yes. Which doesn't have.
Put brackets around two critical points with the same critical value. Put brackets around that phrase. Then it might help.
Do you have an example in your mind of a function which has two critical points with the same critical value?
What picture one?
I'll go to the extra page that we introduced earlier, and so here is a picture of something that what am I doing? Why am I doing this? Sorry, everyone. Live drawing is my weakest point. Right. So this is an example. So if you take this surface and you look at the height function of this, there's going to be those two critical points of the height function that will have the same critical value. And so this is an example of a smooth function with two critical points that has the same critical value. And I want to consider the space of all smooth functions for which this phenomenon doesn't occur. And I'm showing that this space where this phenomenon doesn't, the space of smooth functions where this phenomenon doesn't occur is a dense subset of the space of all.
Also open-ended.
It is also open-ended. I'm not
Not
saying it, so I haven't strictly speaking proved it, but yeah, it is. Yeah. I guess the open condition here is kind of easier to see than.
How on the understanding the English of that sentence
Sorry.
was the function which doesn't have two critical points.
Ah.
Yes.
I see, and I also see now why you urged me to put the parentheses, because I was very confused as to how the parentheses would help. Okay, yeah, no, that's a very different thing. Yeah. Exactly, yeah. Is that now, is everyone relatively happy? Yeah. And then just maybe to pedantically complete the argument, the space of excellent Morse functions is an open subset of the space of Morse functions. And we've proved that the space of Morse functions is open in the space of all smooth functions. Therefore, the space of excellent Morse functions is an open subset. Yeah. I'm just trying to sort of like make clear what comes from the transversality theorem and maybe what doesn't, and how to put those together. But yeah, questions, comments, concerns, either online or in person before we get our bird's eye view of Tom Boardman theory.
Let's just say hi to Dario and just maybe unmute. No questions. Dario says.
Yeah.
And
yeah, I don't have any questions. There's just a lot of notations. At some points, I forgot what a symbol meant, but I'll go look back at it later.
Okay. Yeah, it's I introduced a bit quite a lot of new things today.
yeah, it's going great.
Yeah. So I can tell you maybe roughly how, I mean, I wanted to give you a small gift and sort of like apply like all this machinery to a problem, which I actually quite like. It's this witness.
It doesn't matter if we go over time, because I delayed us.
Let me just, that's okay. Yeah, let's see. It's a cool application. It's not relevant to the story I'm trying to tell, but today was meant to be a bit of like having fun with like hammers. So let's use this hammer to like another construction. So yeah, so far, what have we extensively thought about? We extensively thought about when a map whose target is R is generic. Okay, by generic I mean like the space of such maps is like open and dense. We will soon might mean tomorrow, but we will soon explain what when a map with target the plane is generic. It's like a different, so we're going like one dimension higher for the target. But in this interlude, I want to get us to like the other regime where the target is no longer like of small dimension, but it's of high dimension. And that's the regime of this like Whitney's immersion theory. So recall, just like we had a submersion, there's this notion of immersion where you have a smooth map, it's going to be an immersion at P, the differential is injective. And again, that means in particular that it's a full rank. And F will be an immersion if it's an immersion everywhere. So what is, also, I guess, important thing in this story, I should say, from like everything that we've said so far, F being an immersion means that, oh no, it's okay. The first jet section of F, I guess there's many ways you can say that. Like one way you can say that, like F being an immersion directly implies that SR of F is empty for all R greater than 0, because being an immersion means that at each point a differential of F has full rank. That's the condition of being an immersion. Therefore, like the subspace of M where the differential of F drops rank by R must be empty for all R greater than 0. It's like by definition. And this condition by definition means that J1F intersects all of the SRs vacuously if R is greater than 0. That just follows by this cute little thing that we said, J1 F of X is in SR if and only if X is in SRF. Okay. Okay, so what's Whitney's immersion theorem? Whitney's immersion theorem tells you that if M and N are smooth manifolds, and the dimension of N, so N will be the target in our example, the dimension of N is much bigger than the dimension of M, and by much bigger we mean greater than or equal to twice its dimension. Then the space of immersions from M to N is an open and dense subset of the space of all smooth maps from M to N. And in particular, that implies that it's non-empty again. So it means that I can always find an immersion from M to any space whose dimension is greater than or equal to twice the dimension of M. Okay, let's just prove it. So just from definitions, the space of immersions sorry, I wrote sorry? Yes. Well, you mean here? Yes. But it's also in particular true as a subset. Good question. Yeah. 5 minutes as, yeah, I mean the subspace.
Yeah. Just to say, yeah, that this would be, there's a cool theorem about turning a sphere inside out. So that's where you've got a 2-sphere immersed in, I think, in R4. And
no, it's in R3.
It's in R3. Sorry, it's immersed in R3.
Yeah.
Okay, so that's not the dimension. So yeah, this thing is saying that you can always immerse a 2-sphere in like in R4, clearly.
Yeah.
You can also immerse a 2-sphere in R3, which is also clear. But there's a sort of path of such immersion. So we're gonna have to need tomorrow's lecture to think about that.
Yeah. I can't promise that I'll give you a good answer for that.
Yeah.
I will say something, and that gives me actually, like, your comments makes me want to say something that I will say in a bit.
Okay.
But if I don't say it, remind me.
Okay.
Yeah. so I just posed here because I wrote something in yellow which makes no sense. And so I shouldn't transcribe it in pink, but right. I think what I wanted. What did I want to say? Yeah, I don't know, forget this sentence here. I'll figure it out later. But I don't think it's needed in anything. So yeah. So what does Thom's jet transversality theorem says? It says that the collection of maps whose k-jet section is transverse to all of these guys, the S1, S2, blah blah blah, must be dense in the space of all smooth maps from M to N. And then it's just a matter of computing what the codimension of these things are, which, well, we know it, but the codimension of SR, that's just R squared plus R times N minus M. That was the little formula that I gave you in the first half of the talk. Sorry? Well, it was an absolute, but now I took the absolute value out because I know that the dimension of n is greater than the dimension of n. So that's why I directly wrote it as n minus n. Okay. Well, what's that greater than or equal to? That's greater than or equal to r squared plus rm, because n is greater than or equal to 2m. So n minus m is greater than or equal to m. So I can have this inequality, and that's going to be greater than m when r is greater than 0. Okay, so it means that the first jet space, the first jet section of F will intersect SR transversally if and only if it intersects SR vacuously. So generically, a smooth map from M to N, when N is high enough of dimension, will not intersect, will only intersect as 0. Like its section is only going to intersect as 0. And that's exactly what it means for it to be an inversion. And I think that's actually what I was trying to write here, but yeah. So is that relatively clear where how things work here? We can actually do slightly better. So well, better, I don't know, depends on. We are relaxing the condition, so that might not be better for you, but we can actually think about the sets now of one-to-one immersions, not just like any immersions, but actually one-to-one immersions. So if M happened to be compact, that would actually give us, embeddings. But
draw a picture to explain the difference. We've got one irrational one, of course.
The what?
That you can, because an immersion, it seems weird that a one-to-one immersion is not necessarily an embedding.
Yes.
So just give a counterexample.
Yes. What's your favorite?
Winding, irrational winding of the torus.
Yes.
That's the one-to-one immersion of R. Yes.
Yes. How do you usually draw this example? Yeah. Yeah, that's a good one. So and you want you basically want the slope, like you want to
Yeah.
find a line. That's and you just want the slope to be irrational, and then it will just
it won't be so so that's we'll just carry on with that. We'll draw a few of those. The point is that curve sort of goes on forever. Maybe just draw some more of those, because now it identifies the bottom, which it carries on.
Yeah.
And then eventually the point is that this is a one-to-one immersion of R into the torus. Right? But it's not going to be an embedding, because not image is not a closed. There's a technical distinction between a one-to-one immersion and an embedding.
Yeah, exactly.
So he's not talking about embeddings, which is the thing really interesting. But he is talking about something slightly weaker, which is one-to-one immersion.
But if
but use the numbers that have much further. Yeah. Because like this one we are doing a torus.
Yeah.
Is that a curve on the torus?
Is that a what?
Is it a curve on the torus?
Yeah. I'm defining a map from R to the torus. And well, I'm not drawing like all of the map, but I'm not sure. I mean, I don't know if you want first to draw it, you should just draw it.
Well, what I'm saying is just you just let this line carry on forever. So this goes here, and then that's identified with that, and that's identified with that, and so eventually this thing will just fill out the whole torus, but it'll never. It's not periodic. It's never going to come back onto itself, because that angle is irrational. And so that means that its image, that brown line, is not going to be a submanifold of the torus, because it's like a dense subset of the torus. So that's like a bit of a problem. But like what Filippos was saying is that can't happen if the source manifold is compact. Source manifold here is R, which is not compact, and that's the source of the problem.
And then I'm saying that if the dimension of n was, I guess, a little higher than I asked for it to be before, so greater than or equal to twice the dimension of n plus 1, then I can say that the set of one-to-one immersions, m into n, is a dense subset or subspace, I should say, of same thing to m comma n. And it also happens to be open, but we're not going to prove that here.
So for example, knots are maps or like one-to-one immersions of R1 into S1 into R3.
Actually, embeddings.
But
well, yeah, because they, I mean, yeah, it's the same thing. Yeah.
And so this is when he's saying that the space of knots in R3 is an open dense subset.
No, so knots. Shall I draw one? What's your favorite? Trefoil. Okay. You don't.
Better than me, because the last time I tried to draw something,
it's like it's a trefoil knot.
Yeah.
Let me see if I can. Like figure 8 knots. It's like you take a piece of string, like knot it together, same way you knot your shoes, and in R3, and then connect the endpoints of the string. So you end up with a piece of string with endpoints identified with embedding in R3. That's.
If you did a similar thing in the plane, so if you had a sort of a curve in the plane, then this theorem would be false, right? Because then, if you no matter how you perturb it, if it self-intersects itself, and you try and perturb that away, you can't perturb away self-intersecting. Whereas in R3, you can perturb it.
Yeah. Very good point.
So if we want to be able to do so for knotted spheres, we're going to have to live inside R5. If we want to similar situation.
If you wanna, yeah. Okay. If you wanna say that, yeah, Is it?
Seems a bit weird, but
Yeah.
you have to think 5 dimension.
Yeah, I guess you can't. Yeah, self-intersections are, you can't interpret. Yeah, I have to think a little bit about that actually. Yeah, it's a good point. I was ready to see a proof. So actually, what I'm going to prove is, again, I'm going to use this thing that we mentioned earlier, like an intersection of an open and dense with a dense subset is dense. So what I'm actually going to prove is that in this dimension range, the space of one-to-one maps from M to N is dense. And I'll intersect that with a space of immersions, which we know is open and dense, and get our theory. And we'll focus, we will use again multi-jet transversality. This is going to be now on the zero jet space. So in the zero jet space, I guess I'm defining pi upper 2 of n. So that's twofold zero jet space from M to N. And the target is the twofold Cartesian products. And for W, I'm taking the inverse of the diagonal of N under this map. So it's basically very similar in flavor to like what we did previously. I just, and again, it's like this map here is a submersion, so W is a submanifold. And let's see, maybe instead of like writing it down for the interest of time, I'll make it appear. So again, it's like if J, what it means for J02 of F to intersect W, it means that there exists two different points X, Y in M, such that F of X equals F of Y. That's the, I write here J0, but that's actually maybe a little bit of an overkill. I mean, that's basically just like tuples of like J0 is just like little m comma little n, like basically. And J02 is like tuples of those guys.
So in fact, we didn't need Tom's transversality theorem, but we just need the ordinary transversality theorem.
I think that's
restricted to the submanifold.
Yeah, I might have to think about that, but that sounds correct. Yeah. And so I just basically need to argue for dimension reasons that the only way I can transversally intersect W if I am J0 to F is if I don't intersect W at all. It's basically the same argument that we've seen so many times. It's like, what is the codimension of W? That must be the same as the codimension of the diagonal in N. So that's exactly equal to the dimension of N. Right, the diagonal of N lives in N squared, and itself has dimension N, so 2N. And the dimension of N is greater than or equal to twice the dimension of N plus 1. That's the condition that enters the theorem, which is greater than twice the dimension of M, which is the dimension of the configuration space of 2 points. So we again got that the codimension of W is greater than the dimension of the space of the base. So yeah, it's again the same so far. So I propose that we leave the rest for tomorrow, because it's kind of important to get them right. And yeah, I think it shouldn't matter if in the end we don't get through as much of the proof of the pseudo-isotopy theory. I think this stuff is fun to like do in more detail. But yeah, other questions, comments, concerns? I don't know, how did you enjoy that?
This first time for the Filippos.
I apologize, there are no pictures today, and it's a little bit, yeah, I hope it's still exciting. I find it a little bit hard to maybe draw pictures for a lot of the stuff. A lot of technical definitions that come together. But yeah, questions? Sorry? Yeah. It's not gonna play. You can have a tag to be anything. So you said well, but I'm only thinking about, I only keep track of the smooth structure here. So I guess like the complex plane and R2 wouldn't be like, I wouldn't treat them differently. Like I wouldn't have
What you're really asking is, suppose I have a complex manifold.
yeah, that's what you're really.
Do the Morse theory on an open function.
Yeah, that's what you really are asking.
And there is a thing like that.
I think there is a thing like that which I haven't touched, but
I think this is sort of Stefan Behrens' where there's subsurfaces.
well, but there it was still fairly topological. I don't think smooth. I don't think the complex structure ever showed up. And actually, I'm not. Yeah, I don't really know. I would have to check
The
literature.
varieties, they were like, yeah, I think it was, yeah.
Yeah, no, there it was. I think it was basically
pencils,
well, yeah, but that's true. For those of them, yeah, you can make it translate. Like there are sources when people had to make a translation from singularity theory to selective topology. And I think the most prominent is NITheCS thesis on Ringgold vibrations. But yeah, but I don't know the stuff very well.
So, okay, yeah, let's call it a day, and
Yeah,
we'll meet again tomorrow.
sounds good.
Yeah.
Okay. Thank you for your patience. I think it's okay.
Yeah.